and thank you to everybody. Welcome to the first FI Talk organized by ESA Lab and in collaboration with the ESA Lab Collaborative Innovation Network. I'm representing here with Pi School and Cristiano. I'm a physicist and I'm co-organizing with you this series. And I would like just to spend some words. I will share my screen. What is the CIN, the Collaborative Innovation Network, because many of you are into research in emerging technologies, in Earth observation, and these might be interesting. So let me share the screen. Just I have a few slides. I hope in a while you can see them. Perfect. So I just want to tell you what is the Collaborative Innovation Network. Basically, it's a dynamic community which is managed by in partnership with Pi School that I'm representing, and the goal is to bring together leading researchers to harness transformative technologies and basically to accelerate the future of Earth observation. And why you should take part of this community of people? Because you can catch in time research opportunities with ESA Lab. In Earth observation, you can join a growing global network of experts that are working in AI, quantum technology, neuromorphic computing, with again a focus on Earth observation application. You can find new collaborators and discover emerging trends maybe you are not aware of. And again, as we are organizing today, you can share your knowledge and with the other fellows. And you see through the Collaborative Innovation Network, ESA Lab is attracting researchers in AI, quantum, and more in general, computing technologies. And the idea is basically to start collaborating with the agency and inviting visiting researcher, visiting professor as well. So if you are doing a PhD or you are doing a postdoc, don't hesitate to check our website. I will share it in a while. And again, you will have the opportunity to collaborate with many other interesting people. We also organize workshop talks like this one and events. So this is the first of many FI talks. The next one will be in 2 weeks. And then the third one will be in December. You can find all the information on the website. I will share it in a while, and you can already register. So if you like them, if you want to be part of this community, please check them. They are very interesting. And you can take your phone and save our website or follow us on LinkedIn, and for sure you will be told of new events and opportunities. So thank you again, and I leave the floor to the speakers.
So thank you, Cristiano. Then, yeah, as already mentioned, we're going to give the floor to William, Dan, and Maggie, who are physicists and machine learning enthusiasts working at the particle accelerating experiments at CERN. And they're going to give a talk about how they use machine learning for their experiments. So go ahead.
All right, thank you very much. Can you hear and see my slides?
Yes,
Great.
we can.
Thank you. So thank you for the kind introduction. And yes, we are going to talk about how some machine learning is done at the LHC. And before I start, I just wanted to give us a bit of an introduction as to who we are. So my name's Will, and I formerly worked on the ATLAS experiment at CERN, and I'm now employed at Trillium Tech, which runs this program called the Frontier Development Lab program, which is where Maggie met some of you, I believe, in Frascati, and she is the link that binds this little network together. And there's also Dan Guest, who is also an ATLAS researcher and is the LHC machine learning working group convener. So I think I'll start with asking the question that the ATLAS experiment at CERN is trying to answer, and that is, what are the fundamental building blocks of matter, and how do they interact? And we have a pretty good idea of the answer to this question, and that is the standard model of particle physics. This is our periodic table of the fundamental particles. On the left, you have the quarks and leptons that make up our concepts of matter. On the right, the bosons, like the photon, which correspond to our concept of forces. And in the middle, perhaps the most famous, is the Higgs boson, which is the particle that gives mass to the fermions. And you may have heard people say that the standard model of particle physics is immensely successful. And it is. And what does this mean? So this plot, and I don't want to intimidate you with this, all the things on this plot, but what I really want to draw your attention to is that each one of these data points on the plot, and you can see there's a large number of them, it corresponds to a measurement of some process and property of the standard model. And on the right-hand side is the comparison between the measurement and the theory. And you can see that this ratio is basically 1 within uncertainties for every single one of these measurements. And the absolutely crazy thing is that if you look on the x-axis, this is sort of the rarity of each of these processes, and it spans 15 orders of magnitude. So the standard model is capable of making predictions that span at least this large. It is able to successfully do that, which is incredible. Something else that this plot hints at is that if there are any undiscovered particles, they must be exceptionally difficult to find, or rare, or both rare and difficult to find. So I've just told you how the standard model is exceptionally successful, but it's also got some pretty serious problems in terms of explaining what's out there in the universe. And here are just a few of these problems. So first of all, there isn't a good explanation for the nature of dark matter in the standard model. The picture on the left is a picture of the Bullet cluster. This is a remnant of 2 galaxy clusters that once collided in the past, and the colors show where the visible mass is, the stars, and the purple color shows sort of gravitational mass, which you can get through lensing observations, and they're not in the same place. So this is often taken as evidence for the existence of dark matter. Perhaps most compelling in the middle is the cosmic microwave background. This is a famous plot produced by the Planck collaboration and the Planck satellite. So thanks to ESA for doing that. And from this, this is what tells us that there's a lot of dark energy out there in the universe. And then lastly is the asymmetry between matter and antimatter. So at the time of the Big Bang, we assume that matter particles and antimatter particles were created in equal amounts. And you may know that when they come into contact with each other, they tend to annihilate and turn in themselves into energy. However, that is contradicted by the fact that we exist in a matter-dominated universe. And, there's this big question about where all the antimatter has gone. And although there are some explanations for this in the standard model, it's not enough to explain where we are. So, if you put all of these things together, that's basically most of the universe. And so you could also say this standard model is spectacularly failing to describe that. And so there's pretty strong, compelling evidence that there is definitely more out there. And so how do we go about finding out the answer to these questions? Well, this is where the Large Hadron Collider comes in. It's an enormous machine underneath the French-Swiss border. Its perimeter is 27 kilometers long. You can sort of see how big this is compared to the airport in the bottom right there, and also Lake Geneva. And there are 4 main experiments around this ring. And the one that we 3 worked on was the Atlas experiment, which is sort of labeled at the bottom. I just wanted to make a few comparisons between CERN and ESA. And actually, when I was putting this slide together, I was surprised just how similar they are. Both, roughly 25 member states, about 3,000 staff. And we have our own ways of describing how much they cost. So for CERN, the CERN project is about 1 cup of tea per person per year in the member states, and ESA is 1 cinema ticket per person per year. So I think we're both getting a good return on our investments there. And specifically, we worked on the Atlas collaboration. Maybe this is more akin to something like the Planck collaboration, but this is a bit broader than CERN and is made up of researchers at institutes and universities, CERN being one of those. So there's about 240 institutes from 40 different countries. 6,000 members. And that also means that when we come to publishing papers, the author list is about 17 pages long. And that last comment about the 17 pages means that there's also a lot of organizational structure. I don't want to spend too long on this slide, but we organize ourselves into different groups that do different things. And when you join the collaboration, all members must do a non-physics analysis service task in order to join the collaboration. And this can be anything from building the next detector components, monitoring the existing detector, or doing calibration work. And throughout people's careers, it's expected that people will contribute to some or all of these tasks throughout, and not just do, let's say, the particle physics analysis. And because of this, if you spent time in the control room running the detector while it's collecting data, that is why all members of the collaboration are added to all papers, because they have contributed to them. So here's a picture of the Atlas detector itself. It's absolutely enormous, 25 meters tall. That's something like 11 stories. You can kind of see the size of the people standing on top of it. And it's sort of the size of a football pitch in length. You could fit this. It's sort of a cathedral-sized experiment. And it's deep underground. It's about 100 meters up underground. ESA tends to put things into space, and CERN, we tend to put them underground. And there's lots of different detector components here. I won't go through them, but each one is specialized in measuring either a different particle or different properties of particles. And then together you get measurements of pretty much everything in the standard model. So that was the schematic. Here's some real photos. You might be familiar with the photo on the left. It's quite famous. This was the Atlas detector before it was built. And again, you can actually see, a real person this time standing in it, to just give you an idea of the scale. And on the right is also during construction. These days, it basically fills up the entire cabin, which is underground. And so you can't really get far enough away from it to take a good picture. So these are kind of the best we've got to kind of give you an idea of just how big this thing is. So what does it do? Well, first of all, the LHC accelerates bunches of protons around in a circle, and it's got these two counter-rotating beams. And what these beams do is they come to a focus and they come to a collision point in the center of the Atlas detector. And it is hoped that at least one or some of the protons in each one of those bunches collide, and they collide with such energy that their mass energies are converted into new particles, and then these particles radiate outwards inside the detector. And one of the cool things about this little GIF is you can actually see that there's more than one one collision event radiating through the detector at any one time. The collision rate's 40 megahertz. And so, that's once every 25 nanoseconds. And so it gives you an idea of just how intense this is. And so you might hear us say a collision event. So this is what Atlas does. It takes pictures of those collisions and turns it into data that we can analyze. And this is a snapshot of just one of those collisions. And you can sort of see there's a lot going on here. There are these orange lines. They represent the tracks of charged particles. It's a big magnetic field that that means the charged particles curve as they move. And there are also sort of these highlighted cells. These are hits in the detector where a particle has gone through. And also you'll see that there are these cones, and these cones we group them together into objects. We call these physics objects, so that they correspond to real things. And in this particular case, this cone is called a jet, which is a collimated stream of particles. And you'll see a lot more about these jets later on. So how do we actually go about finding new particles? Well, here's perhaps the most famous example, which is the discovery of the Higgs boson from 2012. And one of the ways this was done is it looked at a Higgs boson that decayed into 2 photons. Now, lots and lots of different processes can produce 2 photons. And so how do you tell them apart from the one that created the real Higgs boson? And you can't really, you have to do it in a statistical way. And so there are lots of background processes that do produce 2 photons. But if the Higgs boson exists and it has a very specific mass, when you add together the energies of those 2 photons, you construct the invariant mass of the pair, what happens is if this particle is real, if this Higgs boson is real, you get this little lump. And that excess is evidence that this particle exists. And that's how we do it. The LHC experiments, they produce a lot of data. And in order to deal with that data, CERN has created the what's called the Worldwide LHC Computing Grid. This has existed since the 90s. It's effectively CERN's own cloud and is indeed the precursor to the modern commercial cloud services. But it works slightly differently. Each research institute pledges resources, but then also gets to use the entire network. And just to give you some numbers, there's sort of 170 facilities over the 42 countries, millions of computer cores, 1.5 exabytes of storage, and the data volume grows by about 200 petabytes a year. Although this rate is actually accelerating, which is causing some people some headaches on where to store all the data. And yeah, data transfer rates of in the hundreds of gigabytes per second. Yeah. So I'm going to now hand over to Dan, who's going to take you through the next part.
Okay, great. Thanks a lot for that intro. Okay, so yeah, I think hopefully now we get a little bit into the sort of where we're going to be using machine learning in the experiments. So we focus on Atlas because that's ours, but there's several others at the LHC which are doing similar things. So yeah, we have a detector. It takes a whole bunch of data. We typically filter the data a little bit, or actually a huge amount, using what we call the trigger system, because we really can't afford to save everything. So there's sort of a fast level of reconstruction that we run there. And then once we've decided to save something that's come off of the detector, we save it to disk, and we'll run sort of a second round of more precise reconstruction, which we just call reconstruction. And the thing that's kind of funny about how we have to do everything is that in parallel, we actually simulate all of the known physical processes because we're looking for deviations from those, right? So we have a whole bunch of physics simulation that we also use, and we feed it in to tune the trigger, and to, we feed it through the standard reconstruction pipeline. And that allows us to make plots a little bit like, this is another example of a mass spectrum on the lower right here, where you see, okay, we've subtracted off some of the backgrounds, but these black points correspond to the amount of data in various bins of the mass. And these filled in colored shapes here represent simulated samples, we say. So in this case, we're actually looking for VH, which is Higgs in association with another particle. And that, that sort of makes one shape. And then there's another shape for another background. And by fitting all of these to the data, we're able to extract some kind of amplitude for various signals. It's sort of the general paradigm that we follow. So next slide, if you will. I think actually we added this because I think one thing we want to make clear is that this happens very much in stages. So Will said something about how we sort of segment the events. We define objects. So there's a whole bunch of machine learning that goes into defining objects within a given event. And then we do further machine learning and stuff on sort of an event by event level. And then I guess Maggie at the end will say something about, doing an even a higher level sort of type of thing to organize all the information. So this comes in several steps. And so it might be a little bit jarring, but try to bear with us. So if you go to the next slide. Okay, so yes, this is with objects. That's what I'm going to focus on. So go on, Will. Okay, so one thing that I've worked on a little bit myself, and so I'm going to focus on that, is the trigger system. So just to justify why we need this, I'm showing the same plot actually that Will showed before, only it's turned on its side. So we have along the bottom, we have a whole bunch of different standard model processes listed. And then we have the probability or cross-section of these happening on the y-axis here. And the thing that you really have to note is that the vast majority of the events that we see in the LHC are basically quark collisions with quarks within the protons. And these form what we call jets, sprays of these particles. And so we see that at something like 10 kilohertz for a fairly energetic jet. It depends very much on the threshold of energy. So most of the interesting physics that we're going after is probably in the electroweak sector. So these are things like producing tops, W's, Z's, Higgs, stuff like that. And this is 3 orders of magnitude lower in amplitude. So we already have, quite a bit of background. And then the really interesting stuff, at least if you ask me, is stuff like producing 2 Higgses, which is somehow much more interesting than 1 Higgs. And this is, several orders of magnitude lower in amplitude still. So, we're going from 10 kilohertz of taking in data to maybe roughly 1 interesting event per hour that we want to keep. So there's a huge filtering challenge. If you go to the next slide. Okay, so there's another way of sort of looking at, this whole challenge, which is just to look at the data flow coming through the detector. So on the detector itself, we have, designated electronics that have to stream out all of the data. And so the data is coming in at 40 megahertz. That's the bunch crossing frequency. And the detector streams it out. The first level of filtering is usually implemented on either FPGAs or also just designated electronics. But we can run a small amount of machine learning or increasingly more as the technology progresses and as the demands increase. We can do some machine learning on this sort of hardware trigger. And that's got to give us a 100 kilohertz output rate. So there's quite a bit of filtering that we do already there. And we have to make these decisions in sort of a microsecond latency. The nice thing is, of course, that everything subsequent downstream of the detector is run in a separate cavern. So we don't have to worry about things like radiation hardness and such. Whereas if we do anything on the detector, it has to have radiation hard electronics. We do some R&D on compression and stuff with machine learning there, but it's a little trickier. After things have passed this hardware trigger, then we run it into a software trigger. That targets something like order of 1 kilohertz output rate, but we can use basically regular computers for that. So we're running either GPUs or just regular CPUs there. And we run pretty much standard machine learning for some definition of standard, but it's, all the software that people are using in industry basically can be used on that level. So as we mentioned before, there's a couple of ways that we do computing. I mean, Will pointed this out. So the stuff that I've marked in blue here, it all has to happen on site at CERN. The stuff that I've marked in red, which is, the reconstruction of the data after the fact, and then also this whole simulation chain that I mentioned before, where we also use generative models and stuff in machine learning. This all has to run on the LHC computing grid, which is sort of an amalgamation of various countries' resources. So there's some challenges in terms of getting everything to run on more homogeneous hardware and stuff. This is especially tricky now that we're using GPUs. It was much easier when in the CPU land, it was basically x86, 64 processors, and now we have to make that all work on different GPU architectures and stuff. So it's an interesting challenge. Anyway, the output from this is basically the objects, which most people use for physics analysis. So I'm going to say a little bit more about some of the object definitions, though. So if we go to the next slide. Okay, say we're trying to find the Higgs boson. That was, one of the big important things at CERN, or 2 of them. I think that's the next big important thing at CERN. The Higgs decays almost immediately. Its lifetime is something like attoseconds. When it decays into 2. Dominantly, it decays into 2 of these things called B quarks. And the B quarks, there's sort of a cartoon of it on the bottom here. They're going to be embedded in a spray of other particles, which we call the jets. So there's various algorithms that are basically responsible for identifying these B quarks, but also other things like, charm quarks and tau. They also are similar in certain ways. We basically have different subdetectors dedicated to everything and different algorithms for everything. But I'm going to talk in more detail about how we identify these B quarks. So if we go on to the next slide, a B hadron decay is basically what we do is we produce a sort of quasi-stable particle. It has a very short lifetime. I'm saying 1.5 picoseconds here. But because it's extremely energetic and because of time dilation, it will actually travel a couple of centimeters from the interaction point. So we have a collision point with a bunch of particles spraying out. The B hadron moves a couple of centimeters. It decays to more particles. Those particles go a little bit further, and that can actually, we'll get a third decay some of the time. And so the challenge is basically to build this signature where we have several subsequent particle decays in a row. So if we go to the next slide, what makes this kind of tricky is that all of this decay happens before we've actually passed through any of the layers of our detector. the first layer of the pixel is of our inner detector is several centimeters out from the interaction point. So what we end up doing is that the particles decay. They decay into these more stable charged particles, which punch through several layers of sensors. And we call the energy deposits there hits. And we can string the hits together and build what we call tracks, charged particle tracks, and extrapolate those back to the interaction point. And so basically what we're looking for is a bunch of tracks that are somehow displaced from the interaction point, which would be characteristic of this decay. So there's a cartoon on the left-hand side. On the right-hand side is this cool sort of image that we managed to take of the detector. And I've just sort of drawn on top of that where the pixel sensors are. You'll see some energy deposited, and you can imagine that if they were, given the angle that I have here, you might see that it actually came from a displaced vertex a little bit away from the main interaction point, which is marked in blue. Okay, so if you go to the next slide. So traditional B-tagging is this B-hadron identification. We kind of had to come up with a bunch of heuristics by which we would take these tracks and we would map it into some kind of a probability of it being, like a B-hadron. There's a lot of other things. There's just regular jets that look very similar if you can't find this this displacement. And we're fighting against resolution and such in the detector. So we had a bunch of heuristics that would say, how displaced are the impact parameters for some of the tracks. We would actually look for the crossing between tracks, and we would try to sort of fit vertices to where these things interacted with each other. But there was quite a bit of sort of hand tuning going on here. And then usually we would take a couple of these algorithms and we'd feed them into sort of a neural network, and that would give us something. So we've been doing machine learning for this, I think, since the first paper that I found on it might have been in like the 80s or 90s, actually, and like detectors before us. It's actually quite old in high energy physics, but it was using this paradigm where we kind of distilled the information into sort of a couple of parameters that would describe things, and then we would feed it into a simple neural network. So what's cool is that with modern machine learning, the networks have gotten much bigger, much easier to train, and the architectures are now sort of flexible enough that we can feed in a lot lower level information. So these days what we're doing is just feeding in the raw track parameters themselves, and then using the simulation which we have, which is pretty good, we can tune the taggers to just identify things that way. Which, if it sounds easy, it's in some ways it is. It's nice because it's just sort of simplified the whole paradigm. We just generate a whole bunch of events and then train extremely big networks, at least by our standards, and then we have our taggers. So if you go to the next slide, I'll say a little bit more about that. So okay, the advantage of ML is that in some ways it's cheap and sort of universal. So what I'm showing here is just a result or a series of results from both Atlas and CMS, which is another collaboration. The y-axis here is basically how much background we're able to get rid of. So it's sort of 1 over the background efficiency. A higher number is better. It means we can throw away more of the background earlier on. So this sort of traditional ways of doing flavor tagging, I'm showing on the left-hand side here, the things we call DL1 and DL1R here. And those were, heuristics fed into simple neural networks. Once we started moving over to what were called graph networks at the time, and then eventually realizing that graph networks were actually, we could actually just use transformers, which are, transformers are kind of the standard thing that people are using in language processing these days and such. We saw a huge increase in the background rejection, and actually at the same time we were able to throw away a lot of these heuristics, or at least not worry about maintaining them so much, the sort of hand-tuned algorithms. So we felt pretty good about ourselves on Atlas for coming out with this, this new neural network that could reject so much background. What was funny is that the other experiment, who we don't really talk to for reasons of just sort of keeping scientific independence, basically did exactly the same thing. They trained another tagger, which uses transformers also, followed the same progression that we did. And I'm not going to really show it here, but we've also retuned this to do, earlier on I showed things like, there's other sort of quasi-stable particles, taus, charms. There's particles that decay into composites of them. We've retrained these taggers, basically exactly the same algorithm on several of these things, and it seems to work quite well in all cases. So that's really quite flexible and nice. Okay, so maybe the next slide. Okay, actually, that's just the end of what I was going to say. So hopefully we have time for questions afterward. Thanks.
Okay, thanks, Dan. So yeah, now just moving on from the sort of object reconstruction type thing. Now I'm going to talk about one of the other things Atlas does. Of course, this is the direct searches for new particles. And here is an example of one of the problems that we might have. So this is another one of those snapshots of a collision event. And actually in this snapshot, you can really see this jet structure where you get these streams of particles that stay in these collimated, jets. And the question is, did this thing come from some kind of new physics process, or is it just something that was already known about in the standard model? And I guess to answer that question, first of all, you need to know, what signal processes are we talking about? And there's an infinite number of them, so you kind of have to find a way to pick one. And this is one that we chose. I chose in one of my searches, and it's complicated. It has to be complicated because, as I said before, if it's not, the things that are difficult to find are the ones that could still be there. And this particular scenario, the two protons come in, and the notable thing about the structure is it decays in these two arms. And so there's a structure to it. And if this hypothetical scenario exists, then there could be 50,000 of these. This could have happened 50,000 times in the Atlas data set. And should it exist, it would have an immense scientific value. It would help answer those questions about dark matter and potentially matter-matter-antimatter asymmetry. So there's a lot of motivation to look for things like this. Okay, so now we've refined the problem. Does this one on the left come from the thing on the right? But then the next problem is, you have to do this 10 to the 11 times because you have to check every single event in Atlas. And that also has its problems. And what you could do, perhaps, let's say classically you could do, is you could look at this decay on the left, and you see that it has this structure. It has this, first of all, the first decay that happens, this first red particle, it decays into 2 quarks, and then another red particle, which itself then decays into 3 more quarks. And so there is these 2 combinations of 3 quarks, and also another 2 combination of 5 quarks that should all add up. See what I mean? But the problem is you could try and do this just using simple combinatorics, and you'd find you need over 12,000 combinations to get this right every single time. And just to contrast this to what the background could be, this is just essentially random combinations of stuff, and the key is that they don't necessarily need to add up in the same way that you have the structure combinations at the top. So this is something you can exploit. But it's obviously also far too slow to do this with a classical approach. So, the machine learning is needed here to make use of the structure in this signal to try and tease it out. And so that's what we did in this paper. And I'd love to talk about this more. We created this symmetry preserving tensor-attention network, which is based on transformers and the attention mechanism, or a modified attention mechanism. And what we did is, we took this signal model on the left, and you can turn it into maths, you can turn it into tensors, and then you could build your network architecture to reflect the structure that you're looking for. Now, in practice, how this works is, each one of these jets that I was talking about, you feed all of those in, they get transformed into some latent space, and then at the end, you have these 2 heads, these 2 different heads to your network, and each one of those heads corresponds to each one of these arms of the decays. And so you classify the jets as belonging to either of those arms, or it just comes from something else that isn't related to this signal process. But the nice thing about this is, okay, I've chosen this particular case, this seemingly random signal model on the left, but you can do this with it whatever you want. As long as you can turn it into some kind of tensor representation, you can build your network, and you can have something that's very good at finding this particular model. And unfortunately, there was no evidence of this new process. But this plot kind of shows you just how much the new method improved the sensitivity. So What you're seeing is just the two mass dimensions of the two new particles that were introduced in the model. And in the middle, this old limit underneath this gray line, that's what used to be the sensitivity. And then, you introduce this new technique and you can see there's a big increase here. So with the same data, we were able to really push out into new territory that we wouldn't have otherwise been able to. And yeah, now I'm going to hand over to Maggie.
Thanks, Will. Yeah, so just keeping in the same vein as, trying to find new physics at the LHC, because the new physics often manifests itself as very complicated signature, and they often look like our background. We're having to be more and more creative with the machine learning that we're using to find them. So Will had sort of talked about how we can use structural information on an event by event basis to sort of tease out those new physics signatures. And now I'm going to talk about an exploratory work that I'm doing right now with some collaborators on using sort of data set wide information. And we sort of tease out these differences by using very large graphs and using graph neural networks on these representations. So next slide, please. So like I said, a lot of the underlying physics processes can impact how a collision event could look when we measure them in the detector. And machine learning is usually used to exploit those event by event differences. However, if we zoom out and look at the entire data set, for example, in the simulated data set, where the pink dots are the signal events from new physics, and the blue ones are the well-known standard model processes, you can suddenly see that, okay, there might be some topological features that we can suddenly see when we zoom out to the entire data set. Next slide, please. And we can further quantify these topological differences by connecting those events in our data set into a graph. And here we can connect the events that are similar or are closer together to form these graphs that now can reveal the differences in the connectivity. So for example, here the pink dots, the signal events, are further apart from each other, so they're more sparse, whereas the background events, they're more clustered together. And we can also, you might ask, okay, how can we define event similarity? What space are we looking at? We can actually define them using simple distance metrics. So for example, you can pick sort of, if you're looking at 2D, which is now, you can pick two attributes of the events that you can measure in the detector and simply measure the Euclidean distance between every pair of events in this data set, and only connect the ones that have distances below a certain value, for example, and form your graph representation of the entire data set. Next slide, please. Okay, so we can connect the events in a data set in such a way, but then you might ask, okay, well, how do we then input a very large graph into, say, a machine learning algorithm? So we have to encode it in some way. And here I'm showing a simple example. So say we have a data set with, say, just 3 events, and A, B, and C. And we want to connect them based on the Euclidean distance between them, like I've done so here in 2D. We can actually then encode these connections into an adjacency matrix. So here, every event is connected with themselves, so that you see the diagonal matrix elements as 1. So the element will be a 1 when there's a connection, and 0 when there isn't. And event A and B are not connected because they're too far apart, so that's a 0. And event A and C are connected, and so are C and B, so that's why they're the corresponding elements there are 1. So now we have formed a 3x3 adjacency matrix which encodes the connections between the 3 events in our data set. Next slide, please. And say when we have a larger data set, say n events, we can basically do this for the entire set, and we get an n by n matrix. And this is something that we can feed into a graph neural network. Like the diagram I'm showing here. So here we can combine the node attributes, which is the X in this diagram, combine it with the adjacency matrix, and we can feed them through our hidden layers, which will perform graph convolutions, which I'll talk a little bit about later. And we can then perform supervised learning using this graph neural network. And in our outputs here, we are trying to perform signal background classification. And the outputs will have a dimension of 2. Okay, I think, Dan, maybe it's just you who can't hear me. Okay, everyone else seems to be able to. Okay, great. Okay, carrying on. So, so really what the addition of this graph encoding in this neural network is what's providing the additional information about the topologies I was talking about earlier between signal and background events. And now let's dive a little bit deeper into what sort of convolutions we are performing in this neural network. So next slide, please. So as we go through the hidden layer, say in the first hidden layer, our node attributes are actually being convoluted by some sort of convolution function. And this could be as simple as sort of averaging. So in the first hidden layer, it's the equivalent to sort of, if you're the central node in orange there, is equivalent to convoluting its attributes with all of its nearest neighbors. And just to give an intuitive sense of what that does to, say, one example attribute is what you can see at the bottom is going from left to right, so no convolution to one convolution. You can see that the distributions between signal and background start having better separation. Next slide, please. As you look at the second hidden layer, so in the second hidden layer is actually equivalent to convoluting the orange node's attributes to with all of its nearest neighbors, but also their nearest neighbors. So you're reaching deeper into the graph, and the resultant sort of distributions in the attributes would be the bottom right graph here, where you see more and more separation between the signal and the background when you say only look at this example attribute. And this is exactly what the graph neural network is exploiting to discriminate between signal and background. The next slide, please. And just as a way of sort of measuring how our graph neural network is performing compared to the baseline deep neural network, on the left here, I'm showing sort of your classic ROC curves, where on the really it's sort of the more your ROC curve is going towards the upper left corner, the better. And we have tried sort of several different convolution networks. So you have the GCN here in green, and then the graph conv model in red. And also we've experimented with different distance metrics. We've used Euclidean distance, the classic one, and also Earth movers distance, which is more physics motivated. We can see some sort of gain that from the ROC curve that our graph is sort of getting additional information from the graph topologies in those graphs representation. But also we measured it in terms of what we call Z significance, which is an important metric when we try to claim discovery, where 5 sigma is what's conventionally used if we want to claim that we've discovered a new particle. And you can see it, so the best JNN model, which is the red one, actually improves this Z significance by 25% compared to the DNN, which is very exciting to us. Next slide, please. And we also are slowly moving towards unsupervised learning via anomaly detection. And this might be something also interesting for ESA, because just from my very brief experience working on Earth observation, there's a distinct lack of labeled data. So maybe unsupervised learning is something that you guys are also trying to move towards. So here the idea is, instead of relying on labeled data from our simulation to inform our ML model how signal event from a new physics process should look like, we can simply detect them as just anomalies against background events. And here is it's a diagram of an autoencoder where we have the adjacency matrix representing the graphs being fed in, and the encoder will try to learn some embeddings in a latent space, which outputs at Z. And then a decoder will then try to reconstruct the original adjacency matrix, which is the graph that we started with. And the goal is to try to minimize the differences between the reconstructed and the original graph. Next slide, please. And again, sort of from comparing a model with graph information in the inputs and without the graph information in the input, we can clearly see that the model is gaining something from these additional topological features that we're utilizing. So hopefully, yeah, this is something that you guys might find relevant in your search as well. I think Ruben had talked about potentially using graph to model river systems for flood prediction. I can see that the size of that graph could be quite large as sort of the graphs that we have here on a data set wide level. So definitely something that would be interesting to discuss later on. And next slide, please. I think I will conclude. I think the main takeaway is that, hopefully you can see that ML is used in many, if not like most aspects of particle physics research at Atlas. We've had 3 examples today from left to right of the object level that Dan talked about, and Will and I had focused more on how we use ML to find new physics, and Will talked about it from like the event level, whereas my work is mainly based on the data set wide level. And yeah, from our experiences, like very distinctly different experiences, we can see lots of applications of ML in the many challenges that we're trying to tackle in particle physics, and also a lot of parallels between what we're trying to do at CERN and what you guys are doing on Earth observation at ESA. So hopefully this is a conversation starter for us to have more crosstalks and discussions surrounding how we use ML. So thank you very much for listening.
So thank you so much. We have some time for question. Maybe to break the ice, I can start with one question. Okay, my background and my heart is still with theoretical particle physics. I'm a physicist as well. So at the beginning, you mentioned that basically discovering a new particle beyond standard model is pretty rare. And using machine learning, and you also mentioned symmetry-based transformer, you showed that you set new higher limits to some particles. And when I was doing my PhD, a hot topic and a beautiful theory was supersymmetry, and there was a lot of hope in discovering real supersymmetric particles. So my question is, do you think, and what's the feeling today at CERN? Do you think that SUSY limits are super high, or do you think there is still some hope for it?
I mean, perhaps both myself and Maggie can answer this question, but I think certainly the paradigm has changed from pre-LHC days. But and I guess it depends how you view it. If to the right of this plot, sort of beyond the yellow band, is of course this unexplored territory, and is a SUSY model that's somewhere in there any more or less valid than the other ones? It depends how you measure it. It certainly could be true that a 1 TeV gluino could still be in the LHC dataset, and it's just sufficiently hard to find. As for the general feeling, though, I mean, I think it's true to say that at least in the lifetime of the LHC project, so that's before the upgrade of the high luminosity LHC, it's unlikely that you would find something, you would have enough evidence to discover something. It's possible that you would have enough enough data to have evidence of something, if you see what I mean by the distinction there. I don't know if you want to comment, Maggie.
Yeah, I think the opinions like at CERN is pretty diverse. Actually, yeah, Dan just messaged me like it's a good point that we actually don't have a supersymmetry group anymore. That sort of disbanded as the popular boy band for so long. But I think these searches have been like quite specific, like at least from someone who definitely had not, well, probably the newest person here out of the 3 of us, that I see a lot more trend into going into like what I said, like anomaly detection, where you don't actually need to have a very specific idea of what sort of new physics you're looking for. You're just looking for anomalies, and that opens up that gives you more flexibility in terms of what new physics you could be looking at. So I think there's there's definitely, I think, being a shift in the opinions, and at least in the approach that we search for them.
Yeah, I mean, I just say I did my PhD on SUSY. I was convinced. I'll just give it a more opinionated answer, which is not reflecting everybody at CERN. I think that the chances of us discovering SUSY at the LHC is extremely low at this point. And that's reflected in how we started out with SUSY groups in every collaboration, and then we disbanded, so to speak. We repurposed them into like search groups. Now, but what I would say about my PhD that was useful is that in the process of doing that, I developed a better tagging algorithm, which was for charm quarks or something, right? And the groups have been reorganized into basically doing, basically anomaly detection. Now, when Maggie says anomaly detection, I think what she's referring to is autoencoders. When I'm referring to anomaly detection, which is I think what, I don't know if anomaly detection is just a buzzword within particle physics, if anyone else uses this. It's a mapping between autoencoder and anomaly detection for some reason. Everything we're looking for is something weird. And the SUSY groups and the SUSY searches and the experiments were great at finding generically strange things. Right? They basically divided up all of the possible combinations of objects and looked for every one of them. And I think that's where the supersymmetry was a great model building kit for that. So I think in general, the collaborations have twisted more toward being like, how do we come up with generic ways of looking for something strange? And that's where all of that research went. And I think it was extremely useful for that reason, as like a model building toolkit. But yeah.
Thank you. Yeah, thank you. I also switched to machine learning and AI thanks to supersymmetry and string theory. So well, that was a positive outcome. And so I don't know if you guys have other questions from the audience.
Thank you, Will, Dan, and Maggie for the talk. I wonder if here anyone has a question. Yeah, Andrea?
Yeah, do you hear me? Yeah, okay. So thank you. That was very interesting. Also, like a throwback to some physics that I did like a long time ago. So going back to the, again, anomaly detection approach that Maggie presented at the end, how do you define what a regular graph is to train your anomaly detection method in order to detect what is an anomaly?
Yeah, so for that, yeah, it's a really good question. Thank you. We train on background only graphs, so we actually only train on the background events, which are simulated. We don't tell them, well, we don't tell the model that these are background events, but at the same time, we also don't include any signal events in our training.
I guess I had a question that goes in the same direction. I imagine that you have like labeled true positives, but do you also have labeled true negatives? And then like, or are you kind of assuming that anything that has not been labeled as a positive, like as a signal for sure, could or could not be a true positive? So then you can kind of penalize false negatives, but not to the same extent false positives.
Yeah.
And that would go in the direction of the previous question, because then how do you know that a background graph really is a background graph?
Yeah, that's a really good question. Thank you. Yeah. So I guess I can answer on a technical side. During the training, there are no labels, so this is completely unsupervised. So it's only in the when we do then sort of validate a model and we say evaluate it on a test set, we'll obviously look at if I say cut on the anomaly score I have at the end, how many true or false positives do I have, and we can use all of those metrics to evaluate our model. But in the training itself, it's background only, and there are no labels. And to answer your question of, okay, when we deploy this onto a real data set, how do we know that, we're training our simulated background events, how do we know that that is a true representation of what a background only real data set would look like? This is definitely something that we're still working on, trying to make sure that our representation of backgrounds in the training itself, which kind of acts as our prior is representative. So this will mean that we have to sort of do a lot of like maybe test on a very small set of real data events to make sure that the model is behaving as we expect, and maybe on top of a small set of real data, we can inject some artificial signal to make sure that then this model is able to pick out those signals from the small sort of real background that we feed it. Does that sort of answer your question?
Yeah.
Yeah, I think so. Thank you very much. So we are almost reaching the time limit. To anyone that already has to go, thank you for attending. Then with anyone that has a few minutes left, I don't know about you, Maggie and William, and then if you have to go very soon, we can wrap up. Otherwise, maybe we can look around for a few more questions.
I can stay a little bit longer.
I can hang out. We never have meetings end on time, so I put
Okay,
2 hours.
likewise.
Yeah.
In that case, does anyone here from the audience have another question? No, does anyone perhaps online have a question? You can ask them, well, either through your microphone or in the chat. Okay, so far, no. In the meantime, I'm curious also, I can ask another question about the anomaly or the event tagging, where you encode the trajectories that was like explained in the beginning. This is like, as you mentioned already, another form of anomaly detection. But I was wondering if you could give a little bit more details in how you are encoding these trajectories, and also then how are you training the models to say whether or not something is an event or a signal. Is it also by contrasting it with the background simulations, or?
Yeah. So okay, I guess I have to. Yeah. So you were talking about this slide, I guess that Will is on right now.
Yes. Yes.
So yeah, I would say, I mean, actually, this is far from anomalous. I mean, a track is like exactly the expected behavior of our detector, right? So most of, like at this level, we do expect all of this stuff to be there. So what we generally do is we have there's sort of a bunch of ways to explain this, but we have the information that is sort of the hit information, which is localized points in the detector, which say where a particle went. And we sort of run an algorithm, which is in some sense like a clustering algorithm. Generally, we just try to extend like sequences of 1 or 2 of those points that are in a row out to build these tracks, right? And that is a whole thing in itself. Generally, the tracks are described by something like 5 parameters. They're kind of helices in the detector, and so that means they have like a perigee point or a closest approach point to the beam line, and then just sort of the rest of the kinematics. So that's the description of the tracks. They're a 5 parameter sort of object. What we do is that we will simulate a bunch of these B hadron decays. There's a bunch of processes that give rise to those B hadron decays, and we'll also simulate what we call light flavor jets, which are basically just any quark that is not a B quark or a charm quark. Actually, probably better. There was an earlier slide that I showed where we show all the different particles, but we simulate like collisions that are basically just those quarks, and they give a spray of particles where nothing is displaced from the interaction point at all. And then we take all of those track parameters and basically spit them out, and then we train a transformer network which discriminates between the ones that had a B hadron inside of them and the ones that did not. And I don't know if that really answers the question, but maybe.
Yeah, kind of. Thank you. That's interesting. So
Okay.
you have like a quite efficient way to encode the tracks by assuming that, or by seeing them as like you encode them by the parameters in
So it's
of an ellipse or like of a shape that lets you encode them through way less parameters than points along the track, or
Exactly. So the design, part of this is the design of the detectors. They're meant to have a homogeneous magnetic field. So then within a homogeneous magnetic field, you would expect a charged particle to follow a helix. And so just because, the detector has basically been designed this way, it works out pretty well to encode all of the tracks as like a 5-parameter object. There's a lot more complicated stuff that we do for, the charged particles will interact with other parts of the detector at some points when they hit layers of sensors, and they'll break apart. So actually the full description of a lot of tracks ends up being far more complicated than that. But for the sake of, especially what we're doing here, where the B hadron is decaying within a vacuum in the center of the detector where there's a very homogeneous magnetic field, the 5-parameter description is usually sufficient. I think the other thing that I'm omitting is like, this is kind of like the standard way that we do flavor tagging, where we look at the tracks. Those particles, when they go out into the detector, they also, depending on what type of species of particle they are, they'll leave different traces in, first of all, the inner layers, which are responsible for building these track helices, but then also there's outside of that, there's like a calorimeter, which will stop the particles, and the shower shapes within the calorimeters can also reflect what kind of particle it was. So one of the things that's sort of been helping, one of the reasons that machine learning has been so beneficial to us is that whereas before these heuristics that we had, they were basically like we could look at, how far away the tracks were from the interaction point. Now we can feed in not just the 5 parameters that describe them, but also all of the information downstream about how they interacted with the detector and such. And so we've actually found that adding in that information, which is not a public result, sadly, will give us another something like factor of 2 in the backgrounds that we can reject. So it's really not just about feeding in the information we started with, but we've actually dug a lot deeper and started to using lower level information. And then in the very far future, of course, the dream is like, well, what if we just get rid of the idea of parameterizing it as tracks at all, and we just say we take the raw information that was in the sensors, maybe we use their location to start with to kind of go slowly, and we feed all of that in. And from what we can tell, like these a sufficiently powerful neural network can kind of learn all of the track sort of fitting stuff that we do and all of that as well. Our detector was pretty much designed to work well for tracking, so maybe it's not necessary all the time, but as like a quick heuristic and stuff like that, it actually seems like it might work quite nicely. And because triggering is all about heuristics, actually, that can be nice.
Very, very interesting. Thank you. I think Sylvester from the online audience has a question.
Yes, I do. Hi, can you hear me?
Yes.
Hello. All right. So one of the questions I have is, how do you calibrate machine learning scores and propagate their uncertainty into the likelihood, fits, and also final systematics?
You're so lucky that you have Dan here, Sylvester.
Well, yeah, I'm not the expert on it, but it's something that we have to constantly deal with because people love machine learning. And your question is perfect because it's like, we just have simulation. We made up a bunch of data and then we train this like super, expressive model on it. Obviously, if we just feed this, if we just take something that is trained strictly on simulation, which we know is imperfect, and we try to use that as though it's actually right, we're going to be totally wrong. So it all critically involves like the segmentation of the events that Will was talking about earlier. So there's symmetries in in the standard model that say that when you produce, say, just to give an example, when you produce an electron, in a lot of cases, you also produce an anti-electron. And depending on the invariant mass of what particle that came from, it's very likely to be coming from, for that symmetry to be followed. So you can do things where you can find, based on what happened in one place in the event, you can actually figure out what some other particle was in a different place in the event. And so using those physical symmetries, we can actually get really pure samples or relatively pure samples of various particles. And so the whole, what we call calibration part of it involves basically using the symmetries that we know about in physics in order to get a pure sample of the particle that we think we're measuring. And then basically we just sort of come up with fudge factors. I mean, we call them scale factors, but it's, we'll parameterize all of our algorithms in terms of how well does it work on simulation versus how well does it work in data? And then when people use it in an analysis, they basically apply like a weight to every simulated event. So actually, somewhere in the backup slides, I don't know if Will can easily find it, I have the plot that we have that had the bar graphs where we keep on training more. It's like right near the end. I don't know if you can find it, Will, but but we made this specifically because we felt like there was so little attention being given to the fact that we have to do a lot of work after we come up with these algorithms. So what's being shown on this plot here is basically like we have fewer of these bars because we didn't actually do the full calibration for every one of these algorithms, but only the ones that we thought were actually worth using. And the points are actually what we measured in data, and then the bars that are filled are what we saw in simulation. And you see that in data it works worse, right? But it still works better, the sort of product of taking that scaling and also taking the new algorithm still works better than what we had before. So, and we also, even in the original algorithms, the modeling and the simulation wasn't perfect. So this is sort of something that we just have to work with. Go ahead, Maggie. Sorry.
Yeah. I mean, I was just going to add, like, sort of when we were making these slides, us three were talking about, like, almost from a research anthropology point of view that, obviously all of these algorithms that you see here are calibrated, and we have, a set of scale factors to account for the differences between the simulation and the data. And these scale factors they're released for everybody to use. If you were to use any of these algorithms in a physics search, you can just grab them and then apply. It's not as easy as that, but basically.
In fact, you have to. The way that the collaboration works, there's no way we would let people publish a paper without using this, basically.
Yeah. But the point is that, these calibrations are once they're done, they're public to other physics analysts. And that's really helpful. That you don't have to basically redo this calibration every time you do an analysis, and these tasks are sort of done, like Will touched upon this, in sort of the Atlas collaboration management, where you need to to be able to become a part of the collaboration, you have to do a service task, and a lot of these service tasks can include, for example, calibrating an algorithm.
All right, thank you very much. Appreciate it.
Yeah, that's interesting. I have one last question that kind of touches upon what Sylvester asked, I think. If you're detecting anomalies, do you have a way to account for uncertainty or likelihood or the degree of anomaly? Or, I mean, I'm sure you do, but how do you build that into your machine learning algorithm?
Was that a question for me or for Maggie? I wasn't sure.
Both.
Okay, yeah.
Or all three of you, perhaps.
Okay. I mean, so the likelihood that we use, the way that it ends up working, I don't know if somebody else has a better answer for this. That's possible. They might go with that. But generally, when we build a likelihood to say that we discovered something, we have to account for all of the sort of uncertainties that we have on every object that we identified. So like what I was saying, this plot that we have here where we're showing, there's a scaling that we do. That also comes with a big uncertainty band on it. And so anybody who's doing like an analysis where they're looking for some kind of anomalous physics, they're going to plug in, essentially, one way to think about it, you run the whole analysis with every one of these, with sort of the high bound for where we think that the scaling might go, and also the low bound. And that becomes sort of an uncertainty in your estimate. So in a lot of cases, I mean, that could totally obscure your sensitivity, right? If there's a large uncertainty on how well we think something is modeled in data, then that basically means, some fluctuation over what we expect would just be invisible. So I don't know, is that sort of the answer that you're looking for, or did you want something more detailed than that?
But then you mentioned, thank you. Then you mentioned that this uncertainty comes from the calibration, right? But do you also have an uncertainty component that comes from your model itself? For example, do you use like the classification confidence, or some more advanced or other way?
I think that's an interesting sort of philosophical question. In the case here, we don't, because I mean, the way that I've always thought about this is the model is a function. Effectively, it's a, you know, I mean, it spits out the same answer given the same inputs every time. And I mean, in that sense, it's no different than any other, you know, mathematical combination of variables that we might come up with, right? So it doesn't necessarily, in the way that we're using it in this case, it doesn't necessarily need an uncertainty. I think there are cases where if you actually do, and another way to phrase this is actually that, so it's just a function, it's a transformation of some of the input variables to the output variables, and we already have derived using, you know, the symmetries and the physics and such, we already have an uncertainty on the output value itself. So to put an additional uncertainty there would sort of be double counting. Now, if you wanted to actually use the output of the neural network without having, you know, this cross check, then it gets a lot more dicey, right? Then, and actually maybe Will has more to say about that. But in a lot of cases, we will just sort of propagate the uncertainties on the input objects through the neural network and hope that the model itself doesn't have that. But it's a very case by case thing, I think.
I don't think. Oh,
yeah.
Sorry.
Well, I was going to say,
No,
the
go
cases
ahead,
that are
go ahead,
problematic is when we try to learn a likelihood directly. You know, there are cases where somebody will try to say, okay, we're going to use machine learning to basically compute like what our confidence is in this. And that requires that the neural network converges the way that we expect it to, according to some, you know, like it mathematically actually does approximate the likelihood. And there you have to do something more complicated. Anyway. Go ahead, Will.
No, I didn't have much more to add other than that. Yeah, you know, for most cases, you know, we have the the uncertainty on the inputs, and that propagates through the machine learning algorithm. The fact that we're using the machine learning algorithm is essentially irrelevant. We wouldn't need, you know, if you did, you could use something non-machine learning, just some classical combination of cuts, and you know, you wouldn't ascribe an uncertainty to the choice of where you placed your selections. So I think I'm just reiterating what Dan said earlier.
Yeah, I understand. Thank you. That's very interesting. Maybe we can more or less conclude the talk. So I want to thank you, all three of you, Dan, Will, and Maggie, for the super interesting talk. I'm going to have to think about some of this, like let it sink in. But sometimes it was really interesting to see some parallels between Earth observation and what you are doing. Like also, for example, the algorithms you're running on like not well on the hardware that are part of the experiment machine, let's say, could be a bit parallel to having onboard like algorithms running on board of satellites. That is something that many of my colleagues are working on. So yeah, I would be happy to be in touch and maybe discuss in a bit more detail some of the topics that overlap or that could be of interest also to researchers here, and that would be nice. Would you mind maybe sharing your slides for the talk so I can share them here, or is that difficult?
I think we can.
Sure.
I was actually wondering
great.
how you guys do that. We use it, all of our slides are usually posted on some kind of internal, like, you know, database of everything. So, yeah. Actually, do you have the slides all posted on the like? I mean, I guess this is the first of a series of seminars. But,
yeah,
I mean,
exactly.
So are you going to have them all public anyway? Because that would be great. I mean, I would actually want to check that out myself.
So if the plan was to make the seminars like accessible to anyone who's interested, at least on the moment, then those of which the presenters agree, because would be put on YouTube. but only if they agree, because we cannot upload on YouTube the seminar of someone that doesn't want to be uploaded on YouTube. So then the recording would be available, and we hadn't thought about that, at least not me, maybe Cristiano had, but it would be great also to have a link there that gives you the slides.
We can think about it, yes, for sure. It's something we can discuss and will be done. Yeah.
Okay. Well, please let us know. You have my consent orally to upload whatever you want, but I mean, it's you can write an email. Okay.
Great. So thank you very much again, and let's be in touch. And have a great afternoon.
Bye.
Thank you. Bye bye.
Bye.